Kunle.
Thank you very much, Jignesh, for that kind introduction, and thank you for having me come to talk to you today at CIDR, especially because I'm a guest to the database community. So the title of my talk is Let the Data Flow, and it's about the way in which hardware data flow architectures will transform computing. So let me begin by talking about the two big trends in computing that you're probably all aware of. The first, of course, is that Moore's law is slowing down, right? So you look at the time between generations of integrated circuit technology, and the length of time to doubling is increasing. The cost per transistor is no longer decreasing the way it was. And you can argue sort of how much Moore's law is slowing down, but there's no argument about the fact that Dennard scaling, which talks about how power scales with decreasing feature size, is over, right? So that means that computation is fundamentally power limited, and the conventional schemes for improving performance based on CPUs are basically stagnated because they're no longer power efficient. So it's no longer power efficient to scale CPUs using the techniques that we've used over time. So the other big trend, of course, is the huge success of machine learning, right? So we're all aware of the way in which machine learning is being used in image recognition and natural language processing and knowledge-based creation, and it's having societal scale impacts in all sorts of areas. Autonomous vehicles, it's transforming the way we do scientific discovery, it's allowing personalized medicine. And fundamentally, this is driven by, of course, training models. And if you want to train very accurate models, you need huge amounts of computation. And if you want to serve these models to millions of users, you also need lots of computation, right? So at the very time that we need all this computation capability for machine learning, fundamental ways in which we provide this performance is running out of steam. And so what does that mean about sort of how we move forward? What sorts of computer systems should we be building for machine learning and other things? In particular, how could we speed up machine learning by 100 or 1,000x, right? So, you've got to do this in the context of Moore's law slowdown, which means the key thing is power efficiency. So it's improvement in performance per watt, not just performance. And if you could do this, then you could unleash a lot more ML applications and capabilities. Of course, the ML space is not standing still, and there's all sorts of innovations in algorithms. And so you need flexibility at the same time you provide this high performance. So, try to take the existing ML algorithms and cast them into hardware to get performance is not going to be the solution. Ultimately, what you want is something that has the performance and efficiency of an ASIC and the flexibility of a conventional processor. And so, in order to kind of come up with a solution to ML systems, ML computer systems, what we need is a full stack integrated solution that looks at how that understands, and exploits the trends in AI algorithms, looks at how data flow and data flow compilation can be used for efficient execution of machine learning and broader data analytics applications like data processing, and then looks at native execution of data flow in hardware, right? And for that, what you want is something like the Reconfigurable Dataflow architecture that I'll describe. So for the rest of my talk, I'm going to describe these three aspects of the solution and how they manifest themselves. So let's start by looking at AI algorithm trends, right? And of course, the most dominant trend is the increasing model complexity and size that comes from trying to achieve more accurate models, right? So a really good example of this, of course, is in the natural language processing space and the use of large transformer models to get state-of-the-art accuracy on all sorts of things, right? And so this trend began sort of in the with BERT from Google AI, continued with GPT-2, and then things really took off in the early 2020 with Microsoft's model, which had 17 billion parameters. And then they came up with another generation of that model, which had 170 billion parameters. And then OpenAI stunned the world with GPT-3 with 175 billion parameters and really impressive language generating capabilities from GPT-3. So the dirty little secret of training these large models is the actual inefficiency of the use of large clusters of GPUs, right? So for the NVIDIA Megatron model, they're using 400 GPUs at 20% efficiency. For the Microsoft NLG model, it's 1,000 GPUs at 6% efficiency. So clearly what's needed is a more efficient way to train these huge models in order to continue the progress in natural language processing. So one of the ways that ML algorithm developers are investigating the use of maintaining high accuracy without having these huge numbers of parameters is to use sparsity, right? To not have all the connections between the neurons. So some people have looked at sort of taking models that have been trained and then sparsifying them. But I think the holy grail is to be able to actually do sparse training. And so key to be able to do this efficiently, of course, is the ability to do sparse matrix multiplication, which doesn't actually work that well on current GPU accelerators. Another place where sparsity is being used is in graph neural networks, right? So this is one of the most exciting recent developments in deep learning. And the idea is to model people, places, and things to train higher quality models. And you're seeing the uses of these type of graph neural networks in all sorts of areas: natural language, social networks, and communication networks. And again, of course, what you get is sparse data access, because of course graphs are sparse, and the need for efficient sparse computation. So one of the benefits of developing your applications using machine learning is that the number of lines of code can be dramatically reduced, right? So a good example of this is the Google translation code, where they went from 500,000 lines of C++ to 500 lines of Dataflow written in the TensorFlow language, right? So the idea that you can build much smaller lines of code. Of course, most of the work is done by the training algorithm, which trains the model and leads to models with huge numbers of parameters, right? So in terms of sort of the languages used to develop machine learning, most machine learning applications develop using high-level domain-specific language frameworks, right? And so domain-specific languages is an area that I've done a lot of work on in the past. And in fact, some of the early work we did on machine learning domain-specific languages kind of predated and shone the way, the path for the work that's being done in some of the languages that are being used here, PyTorch and TensorFlow. And so if you look at these languages, what you get from them in terms of the applications is a data flow graph, such as the one shown here, where you've got a set of operators that are domain-specific operators, right? And such as convolution and pooling and batch normalization. And so it turns out that the work that we did on domain-specific languages about 10 years ago now showed that you could take these domain-specific operators and map them into more generic parallel operators that we call parallel patterns, right? And it turns out that not only can machine learning domain-specific languages being mapped to parallel patterns, but data processing languages like SQL, of course, can also be mapped to parallel patterns. And the key is that you don't want a flat representation, you want a hierarchical representation of parallel patterns. And so just to say a few more words about parallel patterns, and you're all familiar with map and reduce, and others like zip and flat map and group by. And what you have with these parallel patterns are a way of expressing computation in terms of functional operations on collections, such as sets, arrays, tensors, tables, and the like, and a way of capturing the looping abstractions, capturing both the parallelism and the access patterns. And then, of course, this could be optimized to improve performance, right? So if you think about a compiler flow for machine learning or data analytics, right? You start with your domain-specific language application, which uses the domain-specific operators, and then this gets mapped to a parallel pattern intermediate representation, which is a hierarchy of parallel patterns, right? And then one can think about optimizing those parallel patterns using to optimize for memory locality or for parallelism using tiling or a technique we call hierarchical pipelining or meta pipelining. And so then the goal here would be to come up with a optimized representation that could be used to map to some sort of ML hardware architecture, right? So then the key question is sort of what should this ML hardware architecture look like, right? And so for this, of course, you want to take the insights you get from the algorithms, right? So, so clearly hierarchical parallel pattern data flow as this natural ML execution model that you want to accelerate. So this is something that should be executed natively by the hardware. You want to be able to handle really large terabyte-sized models with hundreds of billions of parameters, because of course you want to get state-of-the-art accuracy. I've said that sparsity is important for next generation training algorithms and for graph neural networks. You also want to have the ability to do flexible mapping of your machine learning model to your hardware. So you want to be able to exploit both model parallelism within a particular graph and also data parallelism where you're running different data on the complete graph. And so in order to think about how one defines the interface to the architecture, we came up with a accelerator language that we called spatial, right? And so this is really, we think about this as a way of describing hierarchical parallel patterns in hardware, right? So what do the parallel patterns, how do they manifest themselves in hardware? They manifest themselves as pipelined data paths, right? So, so in this language, you can express parallel patterns as pipeline data paths. You have the ability to explicitly represent your memory hierarchy, because we all know that real performance comes from managing memory. And so you've got to be able to express your memory hierarchy. And of course, you need to have some way of representing this hierarchy of parallel patterns. And so you need hierarchical control. And so this language spatial then is all about allowing compilers or programmers to focus on performance, right? So focus on parallelism and locality. So here's a very simple example of dot product, which of course, comes up all the time in machine learning, right? So here we've got two vectors that we want to take the dot product of, and we're going to use,
I think your slide may be stuck on a previous thing, at least on my screen here. It's on the domain-specific languages slide.
Ah, wonder why. So on my screen sharing.
That is great. Now we can see it.
Okay. I wonder what the delay was there. You good now?
Yeah, we good now. Thank you.
Oh, all right, good. Sorry. So here we have a tiled dot product, right? And you need, of course, to tile for performance. And so because it's tiled, we've got a multi hierarchical reduce, right? And so this looks like in spatial, so you have a way of representing both, where the data is in the off-chip DRAM, how the tiles are represented in the on-chip SRAM, and how data is moved between the DRAM and the SRAM, and the two-level reduce to actually implement the tiled dot product, right? So I don't want to go into details here, but the point here is this notion of hierarchical parallel patterns and explicit data movement and explicit memory hierarchy. Right. And so once you've got an interface like spatial, then you can think about how to implement that efficiently in hardware. And what we came up for this was an architecture that we call plasticine, which is a reconfigurable data flow architecture. And it's reconfigurable in both its compute components that we call pattern compute units, PCUs, and its memory components that we call PMUs, pattern memory units, right? And so you think of the pattern compute units as reconfigurable pipelines, and the pattern memory units as reconfigurable banked memories. And what we showed is that you could take this architecture, and we compared it to a much more fine-grained configurable architecture, an FPGA, which many of you are familiar with, and we got almost 100x improvement in performance and much more better performance per watt. And of course, much better than CPUs and GPUs if you look at the comparisons. And so if you kind of dive into the design of the plasticine architecture, if you look at the pattern compute units, what we see is a nested pipeline of SIMD functional units, right? So here you can exploit parallelism both between across the vector lanes, right? So you can have vector parallelism at any one stage, and of course you have pipeline parallelism across the pipeline. Then of course you can connect multiple PCUs together to get wider scales of parallelism. So you've got nested parallelism capability to exploit. And then if you look at the pattern memory unit, the PMUs, what you see is both separate addressing capability and a multi-bank memory with explicit banking logic. And this gives you the ability to exploit locality because you can get access directly to the data from the PMUs to the PCUs through the on-chip network, and the ability to reconfigure the memory to match the needs of the application, right? So if you need to have more parallelism in your application, then you may, adjust the banking. If you need to do coarse-grained pipelining, then you may need multiple buffering in your memory, and you can reconfigure your memory to suit the needs of the application. So to give you a little more insight into how computation maps to the RDA, let me kind of describe things a little, right? So the really thing that's compelling about reconfigurable data flow architectures is that for data-intensive problems, you can outperform conventional architectures because you can unroll in space. You can extract massive amounts of vector, pipeline, and stream level parallelism, right? So if you think about the loop nest that I'm showing here, right? So you've got an outer loop, for loop A, and two inner for loops B and C, and B communicates to C through some memory, right? As shown here. And so B generates data that is consumed by loop B, generates data which is consumed by loop C. And so if you look inside the body of the for loop, right, you're going to see some number of instructions, and these can be pipelined, right? And so you can execute them in the pipeline. And that means, of course, that you can potentially overlap operations, loop iterations in the pipeline, right? So you've got hierarchical pipelines. You can exploit vector parallelism within each of the pipeline stages. And of course, then you can stream between multiple different PCUs across the network. So if you look at sort of how this works, right, then you can overlap the computation of multiple iterations of any one loop using this pipelining capability. And then what you can do is you can execute the B loop at the same time that you're executing the C loop, which is consuming the data from the last invocation of the B loop, right? And so the way that once you do this, of course, you are finishing one B loop and one C loop every cycle, and so your throughput is going to be X plus Y. And in order to make this work, you need to double buffer your memory. And so the ability to reconfigure your memory to support this is critical. And then, of course, you can parallelize the inner loops and get another factor of M by vectorization. And then you can do outer loop parallelization, where you take the whole of the A loop and you parallelize that and get another factor of N, right? So there's a massive amounts of parallelism that you can exploit using this kind of reconfigurable data flow architecture. And that gives you very efficient performance, because of course you aren't, because you are reconfiguring and then running for a long time, you aren't paying the overhead of fetching and decoding instructions every cycle. So if then you think about the compiler flow necessarily to target this architecture, then what you need is a way of taking the spatial representation, which is a representation of a hierarchical graph of tiled pipelines with an explicit memory hierarchy, and converting it into something that can be used to configure PCUs and PMUs and the network, right? Which would be something that translates the representation that comes from the spatial compiler and generates something that can be used for configuration. So there's lots of details here. I don't have time to go into that, but what you will get once you do that is a data flow graph that's spatially compiled to the RDA, right? And so the PMUs provide the local data access for the input and data weights, and the communication between the graph nodes stays on chip, right? So if you think about a GPU can only do one kernel convolution or a normalization at a time, unless of course you fuse those together. And so what happens is that once a kernel completes, the results are put in the off-chip high bandwidth memory, and then the next kernel has to pick them up. In the RDA execution scheme, the data is transferred very efficiently over the network, and so all the data communication stays on chip, and you get much higher efficiency. So you keep all the compute used all the time. You reduce the off-chip memory bandwidth requirements, and the whole result is higher performance, higher efficiency, lower power, and more energy efficiency. So, based on these insights, about 3 years ago, I and Rodrigo Liang and Chris Ray founded a company, SambaNova Systems, right? And so the idea was to develop a scalable data flow, develop scalable data flow systems for the commercial marketplace, right? And so over the past 3 years, we've built a fantastic team of ML folks, compiler experts, and a set of expert chip designers, and we have designed a system with hardware, compilers, and ML algorithms to actually deliver on this idea of scalable data flow systems. So the first chip that we've developed is called the Cardinal SN10. It's the first reconfigurable data flow unit in history, and it's very aggressive chip, TSMC 7 nanometers, 40 billion transistors, 50 kilometers of wire, hundreds of teraflops, hundreds of megabytes on chip, and direct access to terabytes of off-chip memory. And so, of course, one RDU is interesting, but what you want is a scalable system that can train very large models or use or provide inference for large numbers of users. And so what we have is a DataScale systems family, right? So starting with a quarter rack with 8 RDUs and 12 terabytes of DRAM, a half rack with 16 RDUs and 24 terabytes, and a full rack with 32 RDUs and 48 terabytes. And so with this capability, then you can do a huge amount of both training and inference, right? So the other key thing, of course, is this architecture is as efficient for large batch training as it is for single batch inference. And it's coupled with the reconfigurable data flow architecture and the way in which we execute, we can be very efficient even at batch 1. So in order to actually use this system, of course, you need a software tool train, and the one that we've developed is called SambaFlow, and it takes in models in the common frameworks PyTorch and TensorFlow, does a huge amount of data flow optimization, optimize both the ML aspects of the model, about how it will be executed, how much data parallelism and model parallelism you'll execute, and it can be very dynamic in how it does the mapping to the distributed set of RDUs, right? And so you have both optimization across the RDUs and then optimization within the RDUs. And then what you get then is a efficient mapping of your model spatially to the RDU DataScale system. So what can we do with this sort of DataScale system? Well, we're looking at sort of enabling new capabilities, especially around very large model architectures, right? So, in the areas of very large natural language processing, 100 billion parameter plus models, high resolution deep learning. So the idea here is to be able to build models on high resolution models and then not suffer the accuracy loss that you get when you use lower resolution in order to, because you can't build models on the full resolution images with today's GPU-based computation infrastructure. And then lastly, recommendation models with huge embedding tables, right? Huge embedding tables give you higher accuracy again, and to be able to do that, then you need to be able to have terabytes of embedding tables. And so the capability of very high efficiency and very large memories gives you the ability to do this. So let me tell you a little bit about some of the capabilities that we've demonstrated. So we can train 100 billion parameter NLP models on a quarter rack, right? So in comparison, the equivalent GPU requirements would be, 52 DGX A100s, and so what we can do is with 100 less in terms of power, with a DataScale system, we can train the same size of model. So another example of what we can do is in the area of high resolution deep learning is because we can actually train on the full resolution model, we can get higher accuracy, right? So this shows the benefits of being able to deal with the high resolution directly and not have to lower the resolution in order to fit the memory requirements of the compute infrastructure. So with the RDU, we get higher accuracy because we are doing the training on an image which is 4 times the resolution.
Kunle, your calendar has come on the screen for us.
I thought I turned.
If you hadn't built all these multiprocessors, it would all be single threaded on your laptop. This wouldn't happen.
Yeah, well, you get the what you deserve, right? So with the large embedding recommender systems, we can get higher accuracy and faster convergence because, of course, we're using larger embeddings, right? So the RDU, we use a higher embedding dimension, and so this allows us to get faster convergence and ultimately higher accuracy, right? And in the recommender space, every last bit of accuracy is vitally important for increasing the accuracy of the recommender and driving more business to the particular website using it. In terms of absolute performance, the Alibaba AI Matrix benchmark is a benchmark which is used to evaluate recommender systems. And what we show with the RDU based DataScale system is that we're 5 times faster in training than a GPU and 8 times faster in inference, right? And so what we see then is the ability to reconfigure the data flow of the architecture to match the data flow of the application, and the commensurate improvement in both the efficiency of computation and the use of memory bandwidth allows you to do these very large models and very efficiently, which is something that sort of conventional architectures cannot do. So hopefully I've given you an idea of sort of why ML and data flow and reconfigurable data flow architectures match so well, and what sorts of capabilities this can provide. So next, for the rest of the time, I want to focus something that maybe is closer to some of your interests, which is sort of, what can data flow do for data processing, right? So, one of the things that we are seeing, of course, is the convergence of machine learning and databases, right? So people want to do machine learning directly on their relational data. So the other thing, of course, we're seeing, as I've already mentioned, is the fact that, Moore's law is stagnated, CPU performance is stagnated, and so the future for efficient computation is all around acceleration, right? So we're going to have to accelerate, we have to think about more specialized acceleration in order to improve performance, and that means that we potentially will need to accelerate all the sorts of data-intensive computation that we do. And what we don't want is a proliferation of accelerators. We want an ML accelerator here, a database accelerator there, and an HPC accelerator over there. So what we would like is a unified accelerator that can be used across the set of the applications that we want to accelerate. And so one of the things that we've been looking at Stanford is the idea of a unified reconfigurable data analytics accelerator. And so the idea is that you have a low friction way to extract insights from large data sets. And so you're co-locating database and machine learning processing in a unified data analytics accelerator. So that means that you could accelerate a query such as this that tries to cluster and aggregate records. So both a combination of both SQL and machine learning sorts of operations. And so what kinds of parallel patterns are required for this? Well, you've got to augment the set of parallel patterns that your hardware supports beyond map and reduce, right? So you need some way of doing partitioning, some way of doing sorting, group by, joining, and these sorts of capabilities, of course, are required to implement SQL operations efficiently. So it turns out that you can take the base plasticine architectures, architecture I've described, the P pattern compute units and pattern memory units, and augment the pattern compute unit with a piece of logic we call the DB logic to support the parallel patterns I just described. And it turns out that the increase in area is not that high. You know, in our kind of research prototype, we have a 4% increase in chip area. Now, you know, take that with a grain of salt, but, you know, it's not going to be a huge amount of increase in area in order to support the DB logic. Key to how one does things efficiently is the fact that you want to execute the computation in a vectorized manner, right? And so the key thing then is sort of is how you organize the records such that you can execute them in a vectorized manner, right? So if you think of this picture where the vector lanes are going horizontally and the stages in the pipeline are going vertically, what the key thing to do is to, instead of mapping the records in a horizontal fashion such that you would have different fields on in different lanes, if you did it that way, you'd get lots of cross-lane communication. So the key insight is that what you want to do is you want to organize the data such that the records live within a single lane, and the fields are computed on sequentially over time, right? And so that's what we do. And so you combine this idea with the extra logic, and you can support a number of queries. So these are a set of queries that we looked at, and we implemented these queries on both a augmented plasticine. So the name of the project was called Gorgon. So we had Gorgon, and then we compared it to Apache Madlib running on a multi-socket, I think of a 4-socket Intel Xeon. And what you see is tremendous improvements in performance and energy. So, you know, 3 orders of magnitude improvement in performance and energy. And so this is pretty encouraging to show that, hey, you can take this basic idea of a reconfigurable data flow architecture, and you can, you know, add a little bit of logic, and then you can support various database operations. And the question is, you know, can you go beyond that, right? So if you look at efficient CPU implementations of databases, what you see is they use irregular data structures, right? So they use hash tables, they use trees, they use you know, trees, B trees. And it turns out that these data structures use branches, right? They've got control flow, right? And control flow maps poorly to existing architectures that might be used for accelerators such as GPUs, right? Because GPUs have this fixed vector architecture, which means that if you have a branch, so suppose you've got some vector lanes shown here, and you've got a branch in your threads running on the lane. So you've got the yellow threads are going one way and the green threads are going the other way. So the way that traditional vector architectures handle this problem of called thread divergence, which those of you who've done CUDA programming know all about, is to use predicated lane execution, right? So some of the time you're doing the branch in one direction, and some of the time you're doing the threads that branch in the other direction, right? This is inefficient because, of course, you know, for some fraction of the time, you're wasting your execution resources. So we came up with a neat idea to handle this in the reconfigurable dataflow architecture called dataflow threads, right? And the way to think about this is that we are going to convert control flow to data flow, right? Because, you know, we're all about data flow, right? And so the way that we do this is that in our design is that we take control divergence and we simply filter the threads on a predicate, on whatever the, you know, the predicate that you're using to decide your branch, and you split the divergent threads into two parallel pipelines, and so that you execute both sides of the branch concurrently, right? So the way to think about it is to take those records that I just described earlier for databases and think of them as thread state, right? And so instead of having a fixed number of threads as you would in a GPU when you run a kernel, what you have is a unlimited number of threads that you can create and destroy by, you know, manipulating these records which control the thread state. And so since this is just thread state, these thread states are just records, you can operate on them as if you would, they were database records. You can do filtering, you can do all sorts of things, right? And so then you can use these data flow threads to build computation and data structures. So this is a very simple example where we are, you know, just walking a linked list. There's a more complicated example where you are building a hash table. But the way to think of this then is a way of sort of scheduling the execution flow of your threads in space using the computational resources of a reconfigurable dataflow architecture. And because the underlying architecture that you're running on is this array of computational units that can be used in different ways, this regular structure allows the compute and memory tiles to be able to be used in a scalable fashion, right? So you can trade off the amount of throughput that you need or you want with the amount of compute and memory resources that you have, right? So if you look at these database kernels, hash join, B-tree load, B-tree join, and spatial join, what you see is that we can, you know, by using different amounts of parallelization and different amounts of resources, we can scale the amount of throughput to hundreds of gigabytes of bandwidth. And so we can get to the point where we can make almost any of these kernels memory bound by unrolling and parallelizing sufficiently. So in terms of actually using these data flow threads on a application, so the application that we picked was a ride sharing benchmark. And so here are a number of different queries that we had. So this first query one, you know, matches drivers and riders based on proximity, filters on some conditions, and then ranks by the distance to the driver. In query two, we identify the average ride request count and driver count and over time and at any particular location. And there are a number of other queries too. So the results are shown here, you know, where one is the RDA implementation. The project was called Aurochs. I really need to talk to this student about their marketing, right? So here, you know, the names are kind of strange, and the performance is not. Our performance isn't the highest bar, right? So here we've got one, and we're graphing slow down instead of speed up. But nonetheless, the point here is that if you take Aurochs, which is the RDA with a high bandwidth memory, it's a factor of 100 times better than it's 10 times better than the design that uses DDR, which of course matches the bandwidth difference between DDR DRAM and high bandwidth memory, right? And so what we see is that the performance using DRAM with data flow threads is equal to the performance of a GPU using high bandwidth memory. And then if you look at the performance of the CPU, it's worse again, right? So the point here is that you can use this data flow threads capability to handle irregular control flow and irregular data flow. And so what that means is that there's a much broader set of applications that you can execute on a reconfigurable data flow architecture. So to conclude then, you know, let the data flow. We've kind of shown that you can use that if you think about applications in machine learning, such as high resolution medical images, natural language processing, with huge models and recommender systems using huge embedding tables, they all are data flow problems. I've shown you that traditional data processing problems are also data flow problems. And if you look at the HPC workloads from material science, oil and gas, and simulation, you'll also see problems that basically fit into this broad category of data flow. And so the performance of these applications can all be dramatically improved by next generation accelerators powered by reconfigurable data flow architectures. And so we're excited to see where this style of architecture and this focus on data flow can lead us in the direction of much more capability, much more efficient processing, and improved use of data analytics in all sorts of spaces. So with that, I'll end, say thank you, and ask if there are any questions.
Kunle, that was an amazing talk. The balance between specialization and generalization, beautiful. I know Peter Bonks has a question, so I'm gonna have him ask the first question. And then if you have questions, please raise your hand. We're gonna prefer people raising their hands and come online to ask the questions. The Slack questions can get answered offline, but please raise your hand if you have a question. Peter.
Hi, Kunle. Yes, thanks. Impressive work, amazing talk, and also great that you gave it at CIDR. I see Chris Ree already answering some of the questions in our Slack. Nevertheless, I will ask my question. So my first one. So how difficult is it to support the TensorFlow and the PyTorch APIs on this new hardware? Are they fully supported? And specifically, like PyTorch seems a bit hard because in PyTorch you can kind of intersperse Python blocks with API calls. What is your yeah?
Well, all the existing PyTorch ML operators are supported, right? To generic Python, doesn't run, but
okay.
The core PyTorch is definitely supported. Yeah.
Okay. And well, as a follow-up,
but that's never going to be high performance on any platform, right?
Yeah, that's true. That's true. Also not on GPUs, of course.
Yeah,
Yes.
yeah.
And what happens? What happens? Like, is like space a limitation on these? So if you have very large kind of
Well, you can map it across, so just because we have a spatial architecture doesn't mean we can't do things in time. We can do things in time too. And we can also, go beyond a single RDU to multiple RDUs, right? And we can map the computation across the whole machine in space, if that's what you want.
Okay, of course. Well, I'll keep it to this and leave others also to ask for, because I have many more questions. But back to Jignesh.
Great. I'm gonna sneak in one question, Kunle. How configurable is the underlying hardware fabric? Can you actually literally increase the size and capacity of one of the compute units for memory? And orthogonally, how much time does it take to reconfigure that entire topology if you wanted to set it up differently?
So you have constraints, right? And so you don't have to. So you have you've got a limited amount of memory in any of the compute, any of the pattern memory units, and so you can't go over that. But of course, you can gang them together, right? If you need more capacity, and that the network between them has enough bandwidth so that makes that possible. In terms of reconfiguration time, we haven't announced what that is, but it's low enough that you can dynamically change your algorithm as you run.
Oh wow! Okay, so likely faster than FPGA type of reconfiguration.
Much faster. Don't think FPGA. Yeah, much faster.
Super interesting. That's super interesting.
Yeah.
Okay, I have a whole bunch of questions, but I'm going to give someone else a chance. So Utku, I see your hand raised. So go ahead and ask your question. Be brief. I know there are lots of people who have lots of questions.
Sounds good. Thanks a lot. Thanks for the great talk. My question was, what do you think on using RDU-like hardware for workloads that's not read-only, where you need consistency for data blocks that are concurrently modified with multiple threads?
As long as the computation, it's like any other architecture. We can write. There's nothing that stops us from changing data in both the on-chip memory and the off-chip memory. So yeah, there's nothing that fundamentally limits us from doing those sorts of applications.
Okay, awesome.
Yeah.
That's great. I'm going to sneak in one more question, and then Peter, I'm going to go back to you. So Kunle, as a more general question, even today, when someone takes an intro architecture class, people are introduced to Flynn's classification. Is that completely outdated? How do you teach a computer architecture class now? Do you just skip all of that or present that and say this is all outdated? This looks like a very different architecture. It's like systolic array style, but with reconfigurability, and it's like doesn't fit any of those classifications easily.
Yeah, it's hard to map it into. So it's got SIMD capability, but then it also you can also think that the one part of Flynn's classification, multiple instructions, single data, MISD, you might argue that it's one of those, right? Yeah, we always mention Flynn's classification, but it doesn't really fit neatly into any of the single classes that Flynn defined.
Cool.
By the way, Flynn was the guy who introduced me to Stanford, right? So
I remember that story. I do.
Yeah,
remember.
Mike and I go way back, and so he's been a mentor for a long time. So
cool. So you're trying to put him a little bit out of business, I see, but that's okay. All right, Hamid has a question. So Peter, I'm going to come back to you after Hamid's question. And Pat Helland, I see you online. This may go on as the first conference that you've attended without asking a question. So that's going to go down in infamy. So you have like 3 hours to make up a question at some point. Hamid.
Yeah, so I got two questions for you, Kunle. So
Yeah.
one is there are a whole bunch of companies that they are trying to bring computation into memory. So given the flexibility that you have, is there any room for those guys?
Well, I mean, if you look at the architecture, right, you have hundreds of megabytes of memory on chip and lots of compute closely coupled to it. So if you squint, you would say it is a computation in memory architecture. Now, the problem with kind of putting computation on denser memory like DRAM is that DRAM, processes don't do logic that well, right? And then you've got to be able to cool the thing, right? So, I think we can do fine given that if you think about what future memory technologies are coming down the pike, the future generations of HBM and so on, I think will be fine. But you could imagine that what you'd like is some sort of 3D stack where the higher levels of the stack were memory and the lower levels of the stack were compute. But the lower levels of the stack being compute, you still want it to be something like an RDU.
Cool, wonderful.
So
Okay,
short
can I
answer
ask you
is,
one more?
Yeah.
Go ahead.
Go for it, Hamid.
Yeah. So I got one more question over here for you. So regarding the encryption enclaves, like Intel SGX, how do you fit that into your computation?
Well, I mean, I think we haven't looked closely at what you want to do for encryption, but we can probably figure out how, think about how to actually implement some of these encryption ciphers fairly efficiently in an RDU architecture. Now, explicitly how it gets implemented, I haven't given it a lot of thought.
All right. Thank you. Great talk.
Yeah.
Thank you, Hamid. All right, we'll take one last question. Peter, back to you.
Thanks, Jignesh. Yes, well, I mean, again, it's impressive work, and I actually totally buy into this for machine learning applications. For databases, I kind of look a bit at the history of the GPUs trying to get really a foothold in the data processing area, and while GPUs can handle certain types and certain predicates and certain pieces of database workloads very fast, they have always been hindered by a number of issues. One of them, memory bandwidth, but the other one is that they are not very good at handling like variable size data. They're less regular data types, like even just strings, and strings are extremely common in databases. So how would that map onto RDUs? Would they be able to, because I see
Yeah, so I think the key there is that data flow threads idea, right? And the fact that you could have, if you think about those records, you could have whatever length you like, right? And so that gives you the ability to handle strings or records of that sort.
But it would become variable, like also duration, because the longer the string, the longer it takes to do something, and then things won't work so nicely or neatly in cycle, in pipeline, in SIMD register.
Well, that's the idea, is that if you're doing things in a lane, then you can take as much time as you like.
Okay.
And then if you think about these data, you think about the amounts of computation, right? You say you've got a long string and you want to parallelize that with a shorter string, then of course you need lots of shorter strings to kind of overlap with that long string to make sure that you keep all the pipeline lanes busy.
Well, because in GPU that leads to the lanes.
So in GPU, right? GPU has this fundamental constraint that it is everything has to run in lockstep. Mm-hmm. And you've got this control divergence problem, right? So with data flow threads, we don't have that issue.
Oh, you don't have that issue because you would be able to reload an empty lane with new work?
Right, exactly.
Oh, okay, right.
Cool, wonderful. I really like that last part of the interaction. So Kunle, I know we are a minute over time, and we all saw your calendars. You had 3 meetings at the same time. So just wanted to let you know. Really big thank you for taking the time to talk to us. Chris Ray was instrumental in making all of this happen. So huge thank you to you too, Chris. And with that, we'll end today's session. Thank you, everyone. See you guys tomorrow.
Thank you. Bye.
Okay. I stopped the recording.
I think today went well too. So
thanks, Jignesh. It was